Good afternoon, everyone. Welcome to the Parsons Technical Webinar Series. I'll be your host today, Jessica Bennett. Today we have with us David Patch and Natalia O'Connor presenting on the development and validation of PFAS analytical methods for characterization of complex matrices. If we go to the next slide, we'll go over a few housekeeping items up front. We'll be keeping everyone's audio muted throughout the presentation to keep background noise down. If you have a question, you can enter it into the Q&A section at any time throughout the webinar, or you can hold it until the end if you'd like to ask it live or put in the Q&A at that time. This webinar has been approved for one professional development hour or PDH credit. If you would like to receive a certificate for attending today's webinar, there will be a link to the attendance form posted in the Q&A before the end of today's webinar. There will be 3 multiple choice questions you'll need to answer to get credit. So please take a look at those. They're also posted in the Q&A. And if you have any questions or issues regarding the PDH attendance form, you can contact us following the webinar. And finally, today's webinar is being recorded and will be posted on our YouTube channel in the next few days. So just a brief agenda. We'll introduce our speakers before we have a core value moment to kick off the presentation, before we get into technical content, and then we'll wrap up at the end with Q&A. So a little bit about our presenters today. David is an analytical chemist with experience in both academic and industrial professional environments and has a PhD in chemistry. He has 6 years of experience in environmental research and development, specializing in the analysis of legacy and emerging contaminants. Natalia is a research and development scientist with experience in PFAS remediation. She earned her master's in chemistry and chemical engineering and has 6 years of experience in environmental research and development, focusing on the characterization and destruction of organic pollutants, including PFAS. And with that, I will hand it off to Natalia, who will present a core value before we get into the technical presentation.
Thank you, Jessica. Parsons has 5 core values that are incorporated into all the work that we do: safety, quality, integrity, innovation, and sustainability. Today's presentation will focus on the core value of innovation. Innovation is the heart of Parsons' internal research development program, or the IRAD program. We're always looking to the future and how we can improve all aspects of research, from developing better treatability testing setups, to the investigation of extremely complex waste streams, to developing rapid in-house methods of analysis. We are focusing on PFAS analysis today, and currently, the typical gold standard method is to ship your samples off to a commercial lab for EPA's 1633 accredited method and wait around a month or 2 for results. So it was highly imperative for our lab to develop and adopt a rapid, cost-effective PFAS screening and quantification tool. Furthermore, we use our in-house analytical capabilities for our clients to deliver more robust and comprehensive answers. Before I get too thick into the weeds about PFAS and how we analyze it, I'll back up and give a little bit of background context. PFAS are a group of anthropogenic alkyl compounds classified by their high proportion of carbon-fluorine bonds. These extremely strong and stable carbon-fluorine bonds are what make PFAS so recalcitrant, aka the forever molecule. There have been over 14,000 compounds identified by the EPA, and how we can more easily understand is how they're often classified into different groups based on their context. For example, the synthesis route and how they're made, electrochemical fluorination versus telomerization, their functional end groups, carboxylates or sulfonates, etc. The different applications that they're used in, for example, firefighting foams, AFFF or personal care products and industrial processes, and the regulation statuses. To give a bit more background context on the PFAS assays that we will be talking about today, I'd like to quickly go over the nomenclature and structure of PFAS grouped by their chemistries. We will start with the most well-known PFAS compound today, perfluorooctane sulfonic acid, or PFAS. We can consider 3 major parts of the molecule when looking at its name: its degree of fluorination, its chain length, and its functional group. In the case of PFAS, every single carbon atom is fluorinated, which gives the prefix perfluoro. Next, The carbon chain length is 8 carbons long, which we use to describe using the classic chemistry definition of octane. Lastly, we have a sulfonic acid or sulfonate head group, which gives us the classic sulfonic acid ending. When we put it all together, we have perfluorooctane sulfonic acid. We can now repeat this exercise more quickly for the next couple of molecules. For this molecule here, PFOA, we have a fully fluorinated 8-carbon long carboxylic acid PFAS. So we have perfluorooctane carboxylic acid. However, in chemistry terms, we can replace the end of octane with oic acid as a shorthand. Therefore, perfluorooctane carboxylic acid becomes perfluorooctanoic acid. Next, we have an example of a polyfluorinated molecule. We have 6 carbon atoms that are fully fluorinated and 2 molecules that are not. Therefore, this would be a 6,2-fluorotelmer. The functional group then dictates the type of fluorotelmer. In this case, we have a sulfonic acid, so this is 6,2-fluorotelmer sulfonic acid. For today's discussion, we're going to mainly focus on the PFAS that are typically analyzed by commercial analytical labs. That is to say, we will focus on PFAS within the EPA 1633 suite of compounds, and any PFAS that are outside of this suite we will refer to as unknown PFAS or PFAS precursors. This will allow us to focus on the 40 molecules that are within the 1633 suite that we're most interested in, and avoiding naming molecules that are more and more complex each year. So what does commercial PFAS analysis typically look like? Let's assume that you have a PFAS impacted site of interest and you want to quantify the concentration and type of PFAS present in your sample. However, you aren't quite ready to dive into the 14,000 or so more PFAS compounds. And even if you were, these methods that are commercially available to do that so are incredibly limited. So you decide to focus on more routine analysis. You'll collect the samples, ship them to a lab, and decide what methods you'd like to have your samples analyzed for. Typically, EPA method 1633 is the gold standard for target analysis with 40 PFAS compounds. If you want to really understand an unknown matrix, then you might opt for the total oxidizable precursor assay or the absorbable or extractable organic fluorine assay. Then you'll wait a month or 2 and receive your data where it can be further processed and evaluated for quality. Now you or your client may be asking if understanding and characterizing a sample's PFAS profile is that challenging. After all, I made it sound so easy. You just collect the sample, pick your method, and ship it off to the lab and wait, right? Well, I'd like to walk you through a quick investigation into a C6-based AFFF or aqueous foam forming sample. Commercial EPA 1633 results reported 0.5 micrograms per liter of total organic fluorine. Top assay results reported over 140 micrograms per liter of organic fluorine. And the absorbable organic fluorine assay reported around 12,000 micrograms per liter of organic fluorine. So as we can see here, applying different PFAS analytical methods can lead to more questions than answers sometimes. So why did my EPA 1633 identify only 0.01% of my organic fluorine concentration? Why did my top assay fail and fail to reveal the bulk of the organic fluorine? Can I trust the organic fluorine concentrations? And why did I spend thousands of dollars and wait 3 to 6 weeks for results that I don't understand? And the big question is, how can we avoid this happening in the future? For some of our newest client projects, we've taken a novel phased approach when performing PFAS analysis, finding the right balance between the resource we invest into our analysis and the data outputs we get from that set analysis. We will start by performing screening level analysis to identify the concentration of PFAS present in the samples of interest and how those concentrations change with different experiments. For example, if we have a client that is interested in applying a new treatment technology to their site, we can start off by rapidly evaluating the performance of said technology and identify areas of improvement or optimizations. Once we are confident in the approach, methodologies, and matrix of investigation, we can then send a select number of samples to validate our screening level of analysis. This allows us to send samples with confidence, knowing that our data quality and controls are established before investing the time and money to find out otherwise. Lastly, we can utilize saved resources for a deep dive investigation into the most critical aspects of the project, identifying the key variables that will deliver success for the project and the client. For today's presentation, we will go into detail on 3 analytical methods that we have developed here through the Parsons IRAD program. We've developed a screening level colorimetric active surfactant assay, which can detect anionic surfactants using a UV-Vis spectrophotometer by forming an ion pair with a dye. We have also developed a UV activated top assay, which increases the assay's mass balance performance and allows for a much more comprehensive picture of PFAS concentrations when sent off for commercial target analysis. And last but not least, we have our in-house reducible organic fluorine assay, which quantifies the total organic fluorine in a sample by using a fluorine ion selective probe. This is our workhorse analytical method in our lab and allows us to generate a massive amount of data cost effectively and rapidly. The first screening method we will go over today for PFAS is the colorimetric active surfactant assay, or the CAS assay. The colorimetric active surfactant assay uses a cationic dye to form an ion pair with the anionic PFAS molecules present in your sample. The dye PFAS ion pair is optically active, allowing for it to be observed visually or with UV-Vis spectroscopy. The advantages for this technique is it allows for a rapid visual determination of PFAS concentration. However, the drawbacks are that non-PFAS surfactants and anions can interfere and generate false positives. Here we have the operational parameters for the colorimetric surfactant assay. We've prepared a range of PFAS concentrations in which we have mixed with our dye and extracted using a specific organic solvent. The organic PFAS dye pair is then measured using a UV-Vis spectrometer, which also shows a strong linear relationship between 1 part per billion and 100 parts per billion. We can also try to use our eyes and visually discern the characteristic blue color that increases in strength with increasing PFAS concentration. Depending on how strong your vision is or how good you are at convincing yourself, you may be able to see down to 1 part per billion as well. However, as is often the case with analytical methods, we can have challenges when applying it to real-world samples. In neat PFAS-spiked deionized water, we have a strong signal peak at the left here at 630 nanometers. However, in PFAS-spiked wastewater, we have a second peak that shows up here on the right at 510 nanometers. This second peak is made up of background interference like sulfates, carbonates, and halide salts. This is one of the first methods that we have developed for use in our lab, and we applied it to evaluate the effectiveness of different sorbents in removing PFAS from wastewater. As shown in the figure on the right, we identified a significant removal of PFAS across 5 different sorbents evaluated. However, we did expect a lot better than 82 to 87% removal, and we suspected that the remaining peaks were actually just background interference. We tried a few different methods to remove those background interference, including a salt wash step, in which the interference were removed using a sequential solvent wash. While this did achieve more than 95% removal of the background interference, it also reduced our main signal by about 90% as well. While this method is still very effective for rapid screening evaluation of PFAS, we decided we needed a method that was a little more direct in its approach and a little less susceptible to background interference. The second method we have validated for use in our lab is a UV reducible organic fluorine assay, or the UV-ROF. Parsons' patent-pending catalyzed UV technology has been validated to achieve complete, over 99% destruction of PFAS with around 90 to 110 inorganic fluoride mass balance closure. This technology has been miniaturized for use as an inorganic fluorine determination tool and is referred to as the ultraviolet reducible organic fluorine assay. The UV-ROF assay uses energy-activated reductants to convert PFAS into inorganic fluoride. The advantages of this assay is it has improved characterization of fluorine mass balance, it has a very rapid one-day turnaround time, and it is very cost-effective. However, we do lose loss of sensitivity of PFAS information and specific PFAS information, and we have a lower detection limit compared to other analytical techniques. This technique utilizes the fluorine ion selective probe, which allows for the detection limit of 20 ppb or 20 parts per billion and a quantification limit of 100 parts per billion. However, using solid phase extraction, we can increase the sensitivity by around 50 to 200 times. We have validated the accuracy of this method over the course of several exciting research projects, the result of which we will show in the later slides. The third analytical method utilized by our lab is the UV-activated top assay. Unlike the previous two methods, which can be performed and analyzed in-house, the samples processed by this assay must be sent out to a commercial third-party laboratory for EPA-accredited analysis. Nevertheless, as we will show here, this method significantly expands on the characterizations identified by the standard EPA 1633 and the standard top assay analysis. So why utilize the top assay in the first place? Well, as I mentioned earlier, the gold standard for commercial analysis is the EPA 1633 suite, which analyzes for 40 select PFAS compounds. There are some fluorotelomers analyzed for in this suite, like 6,2-fluorotelomers sulfonate. However, there are many more PFAS present in our world and in commercial products that we use every day that would not be analyzed and detected for in standard commercial target analysis, like 6,2-fluorotelomer sulfonamidobutane, or 6,2-FTSAB, which is found in aqueous film-forming foams, or 6,2-fluorotelomer phosphate diester, 6,2-dipap, which is found in waterproof cosmetics. The total oxidizable precursor assay uses energy-activated oxidants to convert precursors or polyfluorinated PFAS not present in the 1633 analytical suite into carboxylate PFAS that are present and detectable in the 1633 suite. Applying the top assay to a matrix with unknown concentrations of PFAS can vastly improve the PFAS characterization and mass balance. The typical commercial top assay is heat activated. While effective, the standard commercial top assay does suffer from a number of drawbacks, including incomplete PFAS recoveries, which can be up to 50% of loss. It is quite time intensive, from 60 to 20 hours of oxidation. It results in poor preservation of the original PFAS structure, and it can be quite sensitive to matrix effects such as high background organic matter. However, the top assay can be activated with other energy sources, like ultraviolet light. To illustrate the differences between target analysis and commercial top assay and our own UV-activated top assay utilized here in our treatability lab, I would like to walk you through a case study of an AFFF impacted water. The initial analysis of AFFF impacted water sample showed 810 nanograms per liter of total PFAS. Subsequent commercial thermally activated top assay revealed 230 micrograms per liter of total PFAS. The UV activated top assay performed here in our lab revealed 2,660 micrograms per liter of total PFAS. However, there was a significant amount of 6,2-FDS left over, which should not happen after a top assay. This does indicate incomplete oxidation, which we believe is due to the large amount of surfactants present in AFFF, which consumed the oxidant. So to deal with complex samples that have high amounts of background organic matter, we utilize a hydrogen peroxide pre-oxidation step. The hydrogen peroxide is a weaker oxidant and helps us knock out the background organics. And the hydrogen peroxide UV activated top assay revealed a 3,570 micrograms per liter of total PFAS and resulted in complete fluorotelomere conversion to PFCAs. and overall, a 15 times increase in total PFAS concentration compared to the standard thermally activated commercial top assay. And we can see this pattern repeatedly across different AFFF samples and formulations. As shown for a couple of our samples here, C8 PFCAs were generated and detected, indicating a more dated AFFF formulation. I'm now going to pass it along to my colleague, David Patch, to discuss how we've used these advanced analytical methodologies to support client projects.
Thank you, Natalia. So we'll start off with our first client project. There were two major objectives for this project. First was to quantify total PFAS in aqueous film-forming foam and aqueous film-forming impacted materials. The second objective was to validate the PFAS concentrations using a multiple lines of evidence approach. As Natalia has discussed, aqueous film-forming foams are a complex matrix consisting of high concentrations of fluorinated surfactants, PFAS, such as PFAS and 6,2-fluorotelmer sulfonamidobutane shown here, and non-fluorinated surfactants, such as butyl carbitol. AFFF also has several other non-surfactant components, such as alcohols and salts. All of these things can interfere with standard analytical methods, which is why we need better approaches to characterizing these materials. We started off by performing a screening level analysis using our UV-activated reducible organic fluorine assay. We started by preparing the samples to different dilutions to find this sweet spot between PFAS concentration and mitigating the impact of background matrix effects. We then amended the samples with photocatalysts, and the PFAS is then destroyed following activation using UV light. Once the PFAS are destroyed, they're converted into inorganic fluoride, which, following neutralization and buffering, allows the samples to be analyzed using a standard inorganic fluoride probe. Here we have the serial dilution results using our UV ROF assay applied to 3 different AFFF impacted waters. As we can see for the 3 samples, at 2,000 dilution factor and less, we have significant lower amounts of organic fluorine due to the impacts of the matrix effects of our AFFF interfering with our analysis. However, once we see organic fluorine concentrations plateau, this gives us an accurate estimation as the total organic fluorine concentrations present within our sample. We then want to validate these results to ensure that our in-house rapid analytical methods are accurate when compared to accredited third-party commercial labs. So once again, we reperformed our in-house analysis, as well as sending out the samples for absorbable organic fluorine analysis at a third-party accredited lab. We then took the results from the 2 methods and compared them with one another, asking ourselves the major question: does the UV ROF results fall within 70 to 130% of commercial AOF results? So we took 3 different AFFF formulations from our lab, performed our in-house Parsons ROF assay, and then sent out those 3 samples also for absorbable organic fluorine analysis. We identified overall an 83 plus or minus 13% accuracy of our Parsons ROF assay compared to our absorbable organic fluorine assay. Furthermore, the concentrations of organic fluorine found across these 3 AFFF formulations range between 1,800 ppm upwards of 12,000 ppm, which aligns very well with typical organic fluorine concentrations found in aqueous film-forming foam formulations. We then wanted to take a multiple lines of evidence approach to characterize all the PFAS present within these AFFF samples. This involved sending samples out just for EPA 1633 analysis to show what a baseline characterization would reveal. We also performed our UV hydrogen peroxide assisted top assay, which was prepared in-house and sent out to a third-party lab for analysis. To complement this, we also performed our UV reducible organic fluorine assay and validated those results with a third-party absorbable organic fluorine assay. So we took these 4 different methods, applied them to the same AFFF sample, and we wanted to identify, do these advanced methods agree with one another, and do they show better PFAS characterization compared to our standard EPA 1633 analysis. We can see the results for one of these samples shown here. We have our organic fluorine concentrations in our horizontal axis in units of ppm or milligrams per liter. We can see the results of PFAS characterized by EPA 1633 only reveals only a very small proportion of the total organic fluorine concentrations present in the sample. Fortunately for us, our UV hydrogen peroxide top assay, the commercial AOF assay, and our in-house UV ROF assay all show very strong agreement with one another, suggesting that our in-house methods are very accurate in characterizing PFAS concentrations present within complex matrices. Overall, this identifies that EPA 1633 analysis alone is insufficient in characterizing the total PFAS concentrations present within a sample. Standard top assay analysis can underrepresent the concentration of PFAS precursors. Advanced methods, such as the UV H2O2 top assay, can be used to augment standard EPA 1633 analysis. Our in-house screening methods, such as UV ROF, can be used for initial evaluation of organic fluorine concentrations and displays strong agreement with standard commercial accredited methods. Moving on now to our second client project. This was a very exciting project for us. We had two major objectives for this project. First and foremost was to quantify the PFAS concentrations present in complex industrial wastewater samples. Secondly, we wanted to identify effective treatment options to remove the PFAS from that wastewater. To this end, we once again started off by performing a screening level analysis using our UV ROF assay. These samples were prepared using a serial dilution method to once again find the sweet spot between PFAS concentration while also mitigating the impact of our background matrix effects. We then amended our samples with our photocatalysts and destroyed them using UV light activated processes. The samples were then neutralized, buffered, and analyzed using our inorganic fluoride probe. As we can see here, we took two of our samples and analyzed them using our UV ROF serial dilution screening method. We have our concentrations of organic fluorine on the left in units of milligrams per liter, and the dilution factors that we applied on our x-axis below. As we can see here, we reached a plateau in organic fluorine concentrations at a 25-fold to 100-fold dilution factor. This allowed us to identify an approximate organic fluorine concentration of 3.3 plus or minus 2 milligrams per liter for sample 1 and 5 plus or minus 0.5 milligrams per liter of organic fluorine for sample 2. We then wanted to evaluate if we could use different sorbent materials to remove PFAS from the complex industrial wastewater. Taking samples of known PFAS concentration, we passed them through 13 different sorbents to evaluate the amount of PFAS removed using our screening level UV ROF assay. You can see the changes in color to our sorbent materials on the left and on the right after passing 200 bed volumes of our PFAS impacted wastewater through the system. We then analyzed the treated effluent to identify the amount of PFAS remaining in solution, with the assumption that any PFAS that was not remaining in solution was therefore captured by our sorbents. Our figure here shows our amount of PFAS removal as a function of our different types of sorbents applied. We applied 8 different anion exchange resin materials, which are typically understood to show very good success in removing PFAS from complex aqueous matrices. We also applied a cation exchange resin, which actually typically is not expected to remove any PFAS unless the PFAS present are cationic or zwitterionic in nature. We also applied 2 zeolite sorbents, which have been reported in literature to have mixed success for removing PFAS from wastewater. And we also applied 2 GAC or granular activated carbon materials, which are typically seen as the gold standard for removing PFAS due to their large surface area and carbonaceous material. As we see across our 8 different ion exchange resin materials, we saw really excellent removal in IXR materials 2, 3, 5, 6, and 8. As expected, we saw no PFAS removal whatsoever in our cation exchange resin, IXR number 9, and little to no PFAS removal amongst our 2 zeolite materials. However, both of our GAC materials did show above 95% removal of PFAS from our wastewater. With these screening level results acquired, we then wanted to refine our sorbent evaluation. So we performed the same experiments, this time only using 4 of our best sorbents, and reevaluated them using commercial accredited analysis. So once again, we passed 200 bed volumes of wastewater through our material, collected the effluent, and then sent them off this time for analysis at a third-party accredited lab. This is where the advantages of using a third-party accredited lab compared to our in-house methods really shows. Our in-house methods are fantastic for rapid screening level analysis, but you lose the individual PFAS molecular treatment information. So by refining our analyses down and our performance of these 4 resins, we're able to identify PFAS-specific treatment results across our 4 different materials. As we can show here, even though GAC 1 and 2 showed very promising results for PFAS removal across the board, GAC 2 performed significantly better than GAC 1 when looking at PFAS concentrations in wastewater by different PFAS functional groups. IXR 3 and IXR 5, however, both performed absolutely fantastically for removing all the PFAS from the wastewater, regardless of PFAS functional group and chemistry. We then want to identify the sorbent capacity of our 2 different ion exchange resin materials by using batch isotherm tests. When evaluating sorbents for removing PFAS from water, we often consider the first 3 metrics: total PFAS removal, the rate of PFAS removal, and the PFAS mass removed per mass of sorbent, also referred to as the capacity. While total PFAS and the rate of PFAS removed are critical metrics, the capacity is really important when we start to scale up and apply these technologies for client sites and field. You may have a material that removes all your PFAS, removes it incredibly quickly, but if it can only hold a little bit of PFAS per unit mass of sorbent, that material is going to be outshined by another material that can hold 10 or 20 times the amount of PFAS. We can evaluate PFAS capacity by treating the same volume of wastewater with increasing masses of our sorbents. Our post-treated water is then collected and analyzed rapidly in-house using our UV ROF assay. Starting here for our IXR number 3, this is a non-specific IXR designed to grab all anions present within a wastewater. You can see here in our left figure, we have S on our y-axis, which is a measure of milligrams of PFAS per gram of resin. This is effectively related to our capacity of our resin material. On our x-axis for our left figure, we have CE, or concentration of PFAS at equilibrium. This is showing how much PFAS is remaining following equilibrium between our sorbents and our wastewater. We found at breakthrough, therefore 95% removal or 5% of our PFAS remaining in solution, our IXR number 3 had a capacity of 0.74 milligrams of PFOA per gram of ion exchange resin material. In the figure on the right here, we can show the amount of PFAS removed as a function of our mass of our sorbent. And we can examine the area in which our sorbent is exhausted. Effectively, our sorbent has pulled as much PFAS out of solution as possible. And then our area on the right, which shows that our PFAS has been depleted. And we have additional space on our resin to hold more PFAS. Overall, these results for IXR3 were lower than we expected. However, this is due to the fact that this complex wastewater sample has a lot of other components present within it that are competing with PFAS for binding to IXR3. We then evaluated IXR number 5, which is a PFAS-specific ion exchange resin. Once again, our figure on the left shows our PFAS capacity in S in milligrams of PFAS per gram of resin, and our x-axis concentration of PFAS at equilibrium shows how much PFAS is remaining after our batch absorption isotherm test is complete. Overall, we identified that IXR5 has a capacity of 4.32 milligrams of PFOA per gram of IXR, almost 6 times higher than that of IXR3. As we can see in the figure on the right, we needed much less sorbent to pull the same amount of PFAS out of the water. And even at breakthrough, we still managed to achieve 86 to 98% of PFAS PFAS removal before reaching our exhaustion point. IXR materials are fantastically effective for treating PFAS from complex aqueous waste streams. However, they result in a highly concentrated secondary waste stream, in this case, solid PFAS-loaded resins. Typically, these IXR resins are disposed of after use, resulting in a consumable product that has to be managed constantly over the course of a client site treatment. However, IXR materials can also be regenerated using different chemicals and solvents to restore the resin effectiveness. For our investigations, we evaluated 3 different reagents in an organic water co-solvent blend and varied the concentrations of those reagents to identify our ability to achieve PFAS regeneration from this material. As we can see in the image on the right, the image in the top right corner is our IXR material after loading of 400 bed volumes of wastewater. The material is very dark as it has loaded a lot of PFAS and has been fouled by a significant amount of non-PFAS components within the wastewater. In this example here, we used one of our reagents in our regeneration blend and pulled off a lot of the PFAS as well as the foulants from the material, restoring the color and the effectiveness of our ion exchange resin material. Using the UV reducible organic fluorine assay, we can characterize the amount of PFAS recovered in our regenerants as a function of our reagent concentration in our solvent blends. In our figure shown here, we have our PFAS regeneration from IXR number 3 on our left y-axis, ranging between 100 and 120% total PFAS recovery. On our x-axis, we have increasing concentrations of our reagent in our solvent blend, with reagent 1, reagent 2, and reagent 3 being different types of salts that are added to our solvent. As we have shown here, at concentrations of 100 millimolar of our reagents and higher, we're able to achieve 90 to 110% of PFAS regeneration from our IXR3, presenting a very attractive option for recovering PFAS from our regenerant and restoring the usefulness of our IXR material for subsequent treatment on our client site. However, this does result in a liquid PFAS-enriched secondary waste stream. Fortunately, we can manage this liquid secondary waste stream through using PFAS destruction technologies. We evaluated the Parsons patent-pending catalyzed UV technology, as shown here on the right, for the destruction of PFAS in this PFAS-enriched liquid secondary waste stream. If anyone is interested in more details about this destruction technology, I encourage you to go to the Parsons YouTube channel and look at the 2025 webinar titled Reductive Defluorination of PFAS using a UV photochemical reactor. However, in brief, we took a 3-step process to evaluate the destruction of PFAS-enriched regenerant. For our step 1, we performed our loading cycle, in which case our PFAS-impacted wastewater was passed through our IXR material, resulting in PFAS-free effluent. We then regenerated our IXR material by passing one of our regenerant blends through our IXR material, restoring our IXR effectiveness, and removing all of our PFAS into our regenerant. We then took this PFAS-enriched regenerant that had a concentration of 30 milligrams of PFAS per liter and passed it through our catalyzed UV destruction system, where we monitored the PFAS destruction as inorganic fluoride coming out in our monitored effluent stream following destruction in the catalyzed UV system. We identified over a 15-minute period 103 plus or minus 8% destruction of that PFAS measured as a concentration of inorganic fluoride. This demonstrates that through our combined analytical approaches, we are not only able to show complete destruction of PFAS, but achieve complete mass balance closure of that destroyed PFAS as well. Concluding our client project number 2, we identified that our in-house analytical methods using specifically the UV-ROF assay can be used to screen for initial performances of PFAS treatment materials such as sorbents. The best materials can be evaluated at third-party labs for validation and PFAS-specific performance. Treatment technology performance metrics, such as rate of treatment, treatment capacity, and management of secondary waste streams, can be characterized using in-house methods, allowing for rapid optimizations before applying our third-party validation. We have our operational parameters summarized for our UV ROF and CAS assay shown here. As we can see, the UV ROF assay has a higher method detection limit and quantification limit, but results in direct organic fluorine quantification, providing strong confidence in the results when they're applied to PFAS impacted samples. The main drawback of the UV ROF assay is if there is significant inorganic fluoride already present within the sample, this does require solid phase extraction or SPE to clean up the sample. This has the added advantage of also improving our detection limits further. For the CAS assay, it is a more rapid method with lower detection and quantification limits, and its strengths is it is a total surfactant analysis. So it will tell you the concentrations of PFAS and non-fluorinated, non-PFAS surfactants present within your sample. However, that strength is also a weakness. If you are only interested in your PFAS surfactants, you may need to do additional methods to remove your non-fluorinated surfactants from your sample. That often will result in the use of the UV top assay to oxidatively destroy your non-fluorinated surfactants, leaving only your PFAS behind. We also shown several pre-processing techniques. The focus of today's presentation was the UV hydrogen peroxide assisted top assay. The method detection and quantification limits of this approach are method dependent, and while it adds a small amount of cost and turnaround time per sample, it significantly improves our overall PFAS characterization when sent out to a third-party commercial analysis for EPA 1633, and it also improves detection limits and reduces background interference for coupling to in-house analytical techniques like the UV ROF or CAS assay. Overall, concluding our presentation here, the use of advanced analytical methods in support of client projects allows for project budget savings of approximately 20%, with a significant increase in data output, between 200 and 500% increase in overall scientific output across a client project. The developed UV reducible organic fluorine assay allows for rapid screening level characterizations of the total organic fluorine concentrations present within the water. The enhanced UV top assay or UV hydrogen peroxide top assay provides a comprehensive characterization of unknown PFAS compounds present within complex samples. These methods, as shown here, have been validated with commercial EPA 1633 and AOF assay analysis. And we are currently modifying many of our methods for portable field deployment to client sites in Q1 2027. So with that, we'd like to thank everyone here for taking the time to attend our webinar presentation, and we'd be more than happy to take any and all questions.
Thank you very much, David and Natalia. It was a great presentation on the challenges, but also some new developments for PFAS analysis in these situations. If there are any questions, you can raise your hand if you'd like to ask it live, or you can enter it into the chat, the Q&A feature, and we will read it out. So it looks like we got a couple that have come in. Have these methods been applied to materials other than AFFF and wastewater?
Yes, we've applied them to several other materials we haven't shown here. We applied them to soils, commercial products, textiles, AFFF impacted solids, drinking water, something we're working on right now for application to, as well as collected air samples. Our AFFF and wastewater data sets are the most robust, which is the ones that we present here today. But with initial optimizations on the front end, these methods can be applied to really any kind of sample of interest. The major limiting factors that need to be considered when applying to new matrices is the initial concentration of PFAS present in the sample, as well as how complex the sample is from a chemical and biological standpoint.
All right, great. Thanks, David. The next question we have is, What matrix components can interfere most with the UV-ROF assay?
I could take this one, David.
Please do.
There are several matrix components, including turbidity as a general, and then anything that can influence turbidity. Also background organic matter, metals, and nitrates, and things that can consume aqueous electrons as such. But we have methods, pre-processing methods to handle all these background interference.
Okay, looks like we have a question asking, are there plans for these methods to be validated for drinking water analysis?
It's an excellent question. We are indeed working on modifying and validating these methods for drinking water. One of the biggest challenges in drinking water analysis, as has been discussed a little bit, is the regulations around PFAS in drinking water are in the order of parts per trillion. And these methods, while fantastic for screening level approaches, have detection limits about 1,000 to 20,000 times higher than what is often required for drinking water analyses. We can get around that by using standard solid phase extraction and high volume solid phase extraction methods to effectively remove and concentrate the PFAS from that drinking water stream, and then applying it and then extracting that PFAS from the SPE and applying our in-house methods accordingly. There's always going to be a balance of resource investment in versus data output. And oftentimes, as the case with drinking water analysis, we want the utmost confidence when characterizing the PFAS concentrations present in our samples. Our in-house methods could absolutely be used for a screening level characterization of PFAS present in drinking water, but these results would need to be validated using accredited third-party commercial analysis to not only identify the PFAS profile, so what types of PFAS molecules are present within your sample, but to also reach those really stringent detection limits required for drinking water samples.
Okay, looks like our next question is, what would you use to extract PFAS from solid matrices such as soil?
That's an excellent question. This is a really great example of the challenge in using accredited methods versus staying agile with the academic fields. So in the case of soil samples, it's typically understood that we need to use a methanolic regenerant solution with a small amount of salt, such as ammonium hydroxide or sodium hydroxide present within the sample. And the EPA 1633 method reflects that accordingly. However, there's been some really great academic publications in the past 5 years that have identified that depending on your soil chemistry and soil composition, you need to employ either really aggressive methanol extractions with really, really high salt concentrations, or you need to use other variables such as heat or changing up your solvent entirely. So to answer the question directly, it's really going to depend on your soil type and your PFAS type present within your sample. You could use methanolic-based extraction methods. You could use high base extraction methods. There's also a move to use supercritical carbon dioxide to remove PFAS from soil matrices. It's a fantastic question. It's going to be highly specific on your soil type and your PFAS composition. And that's where methods like this really come in handy. You can do in-house spike experiments where you add a known amount of PFAS to your soil and then apply different extraction methods to see which of your methods give you the best PFAS extraction results off the bat. You then send those samples out for third-party analysis to identify what's going on.
Okay, and we have a kind of a follow-up question to that. Under what scenarios would laboratory analysis only be more applicable?
Excellent question. It really comes down to detection limit and depth of information. So if you want PFAS specific concentrations for each of the different 40 PFAS within your suite, and you need detection limits in the range of, below parts per billion, closer to parts per trillion levels, commercial analysis becomes more and more attractive. The methods that we've presented here, the UV-ROF and the CAS assays, are really great for a total chemical group characterization, either total organic fluorine in the case of UV-ROF, or total surfactant in the case of the CAS assay. And while there are modifications that you can do to further narrow and specify these methods, at some point you're going to be doing so much pre-processing that you are just better suited for sending it directly to a commercial lab, assuming that you're okay with the 3 to 6 week or more turnaround time.
I've got a question about how are any of these methods usable in the field for rapid screening? Are they portable in the field, or do you have to only do them in the laboratory?
It's an excellent question. Thank you for asking that. Right now, we're looking at the UV-ROF assay as being the most attractive option for field deployment. This is due to the fact that the solutions and the reagents used in the UV-ROF assay are innocuous and very safe to handle. And the biggest thing that needs to be managed is UV light, which can be managed very readily in the field. The energy consumption required for the UV-ROF assay is very low. So this could be run off of a portable power pack or off of a small generator. And this would allow you to do on-site characterization of your PFAS and organic fluorine concentrations on-site. This is really fantastic for delineating PFAS spills, delineating PFAS plumes in soil or water environments, and confirming the effectiveness of on-site treatment options.
Okay, looks like we got another question just came in. With all these different methods, how do you ensure that the results are accurate and comparable across the site?
It's an excellent question. We take two different types of approaches for ensuring our data is accurate and precise. The first and foremost, as we've shown here, is we always validate with commercial accredited analysis. We're always going to send a subset of samples out to a commercial lab to ensure that our results are the same. If the results are the same, that's fantastic. In scenarios in which they aren't, then we can do additional analysis to see where that deviation occurred between the two different data sources. As well, we have a very robust quality assurance program that we use that is baked into our analytical methods. So everything from reagent blanks, method blanks, organic fluorine spikes, inorganic fluoride spikes, surfactant spikes, all these different types of quality assurance samples that we carry throughout the method so that we can ensure that internally our methodologies are very effective and aren't failing any of those QA/QC checks.
Okay, well, if anyone thinks of any other questions that you did not get a chance to ask today, feel free to reach out to our presenters directly. David, if you can go back to the question slide.
Yes.
So the email addresses for both the presenters are shown here. And if you can go to the next slide. So our next webinar will be on August 12th on uranium mine and mill cleanup, challenges, remediation strategies, and lessons learned, presented by Kyle Vikstrom and Edward Greiner at the same time, 12:30 to 1:30 p.m. Eastern. Thank you to everyone who joined us for today's webinar. If there's any issues that you have with the attendance form, feel free to reach out to us. We'll also have the recording posted on our YouTube channel in the upcoming few days. And we hope to see you again in August. Thank you very much.